Great. So in this talk, I'm going to talk about how can you utilize the eye tracking data of the people, response time of the people, and model that information to really understand the decision-making process of the people. And also, I want to argue that discrete choice models are not a good framework to do that. So that's why we have to go beyond discrete choice models to be able to incorporate this new information in our models of decision-making process, right? Good. So this is a joint work with Vladimir, who is a research fellow in my group, Jia Zwan, who is a PhD student. She has done a lot of work in conducting the surveys. Xinwei Li, who is also a PhD student, who is a statistician by training. And she has done a lot of theoretical work that I'll be presenting. And Eugene Kim, that most of you might know already. He actually started this work with me when he was a research fellow in my group. So he has also made important contributions in the early stages when I started thinking about this direction. Okay, so there are 4 questions, bigger questions I want to talk about in this talk. The first one is, why should we adopt models from cognitive psychology, right? What is so special about them? Second, what is the underlying mathematical formulation of these models? So I'll give you some intuition. You don't need to know all the maths, but I'll try to explain what's the underlying formulation. Third one, what are the challenges that these models still didn't become the mainstream, right? So you might feel, after I try to convince you, you might feel, oh, these are really good models, but no one uses them except psychologists, right? And the last one is how we are addressing these challenges right now to make these models mainstream, right? So let's start first that why do we need the models from cognitive psychology? So if you think about the discrete choice models, they focus on mainly the final choice. They try to model the final choice. They are fairly static in that sense. What happens when the stimuli is shown to the person and then they make the decision? That period, what happens, they don't care. They care, oh, the stimuli was presented to that choice situation was presented to the person, and this is the choice person has made. But how that person made the choice, it's not much of a concern in the discrete choice models. Second thing, and that's why the information data, the information acquisition process data is difficult to incorporate in the discrete choice model. Another important thing is there are a lot of nudging strategies that people use in marketing and many other parts of the literature and I will talk about one of the nudging strategies, but these models can better capture the effect of those nudging strategies. So just to give you an example, if you think of early Starbucks, they used to have a small coffee, which I call competitor, and the largest coffee, which is target. And then they used to have this medium-sized coffee as well, right? Which will have a lot of difference between the quantity if you look at compared to the large coffee, but the price difference was not that much between the large coffee and the small coffee, right? So if the price difference is not that much, you can see that if you introduce this medium coffee, if someone compares this medium coffee with large coffee, then they will automatically start thinking maybe large coffee is better, right? Because I just need to pay $0.5 more to get the large coffee. So what this medium coffee is doing, medium coffee is making the large coffee attractive, right? And this is called the decoy effect in the psychology literature and in the marketing literature. Right? If you give these kind of choice experiments and when people make choices, discrete choice experiments fail to explain the preferences for the target alternative. So remember, this is the small coffee is competitor, large coffee is target because you want to increase the sale of the large coffee, and the medium coffee is the decoy, right? So the effect of the decoy on the sales of the target are hard to predict using discrete choice models, but those can be predicted better using models from cognitive psychology, and I'll try to demonstrate that as we move forward. Okay. So let's try to understand that, okay, models from cognitive psychology can handle all these issues. They can incorporate the information acquisition process. They are not static. They also have ability to handle these decoy effects, right? So sounds interesting, but how do they do that? Let's try to understand how does the traditional models from cognitive psychology works. So what you see here is a binary choice situation. Think about it as a binary choice situation. And this is the stimulus onset. That means someone is seeing the choice situation, right? That's the stimulus onset. And x-axis is the time after that, okay? X-axis the time elapsed, right? And this is and then this is the point where people make the choice, okay? This is the choice, okay? So x-axis is the response time axis. So whenever something is shown to the respondent, there is some delay between when they start making the process, right? And the axis above this is the evidence in the favor of the alternative 1, and this one is the evidence in the favor of alternative 2. So what this means is, when they start thinking about the choice situation, alternative 1 has little bit more evidence than the alternative 2, right? Because it's above 0. So alternative 1 is already have little bit more evidence. That means it's like, if you think about alternative specific constant, it just means that alternative 1 is little bit more preferable to the person when they start compared to the alternative 2 or product 1 or product 2, right? Now, what these models assume that people start accumulating the evidence in the favor of each of the alternatives as the time processes, right? How do they accumulate the evidence? Maybe they compare the pair of attributes of alternatives, or they compare the attributes across the alternatives, and they keep accumulating the evidence in the favor of alternatives. The common assumption is that at each small time step, the decision makers maybe compare the attributes of alternatives, and whichever alternative wins that comparison, the evidence goes in the favor of that alternative. So in this process, they keep accumulating evidence in the favor of each of the product 1 and product 2. And finally, there is a threshold for each of the products or the alternatives. And whichever these accumulators hits the threshold first, that alternative or product wins the race, and that is chosen by the consumers. Now the question is, does it happen actually like this? Probably yes, but the point is, this is a whole decision-making process, showing someone to something, someone to choice situation, and finally making the decision, right? So the thing is, if you look at this process of accumulating the evidence, in this process you can easily accumulate the eye tracking data, right? Because you can decide, you can incorporate the probability of comparing attributes and then winning that comparison by an alternative in that time step, right? Second thing, you have this response time automatically accounted for, because you have this element of touching that threshold, right? So you have response time automatically accounted for. So if you look at the parameters which are interesting here, is the drift rate, which is how fast you are accumulating evidence in the favor of an alternative. Decision threshold, this is like for each product, what's the decision threshold? Starting point, which is like an alternative specific constant in the multinomial logit model. And non-decision time, which is very psychological thing. Maybe non-decision time is useful when your response time is less than 1 second. But if your response time is large enough, then non-decision time is generally not very important for the practical economic decisions. Non-decision time is not so important. So how do you create models using this idea? So what people do is people make different assumptions of how people accumulate evidence. And based on these structural assumptions, you create the different parametric models, right? So most common models that you have is the multi-alternative decision field theory, which came in 2001, multi-attribute linear ballistic accumulator model, which is called MLBA. Sorry, very complicated names, but I'll be calling that MLBA. Then the most recent one is multi-alternative decision by sampling. The difference in all this, how they model this evidence accumulation process, okay? And as I said, it can handle the process data, right? They can easily, you can incorporate the process data in the drift rates, right? Then you can have as I said, there is a cognitive underpinning of these models. Psychologists claim that these models are aligned with how neurons fire in the brain when people process information. So it has a cognitive underpinning. And as I said, can explain those nudging effects better. But that has been mainly shown in the psychology literature, not so much in the economics literature. I'll show you some studies that in the discrete choice setting as well, they do better. Okay, so let's first try to understand how these mathematical formulation of these models work. So I'll give you two examples, MLBA and MDBS, to try to explain you how do they really define the probabilities, unlike the traditional discrete choice models, okay? So let's try to see how it works. Let's first try to understand the concept of MLBA. How do they do this formulation? So let's say there are three alternatives, X, Y, and Z, right? And generally MLBA assume a common threshold for them. And these X, Y, and Z are the accumulators. Like these alternatives are trying to fight the race, and which of the alternative reaches to that threshold first, that wins the race, basically. Okay, so we have to define few things. The starting point of them, right? Then how do we define the drift rate? That's important. And if the drift rate and starting point is defined, then we can figure out that how these accumulators will reach to the threshold. Okay, so let's first try to understand how do they write the probability expression. Okay, so in MLBA, the probability of choosing an alternative by a response time t, how will you define that? It is defined in this way. What does that mean intuitively? That the alternative I, which has been chosen, should reach to the threshold by time t, but all other accumulators should not reach to the threshold by time t. Then the alternative is chosen, right? So it's a competition between the different accumulators. So now we haven't defined the FIT, which is the probability that accumulator I or the alternative I will reach to the threshold by time t. But let's say we know that expression, then this is how you will write the joint distribution of choosing alternative I by response time t. Okay, so this is how you think about the problem. Now, how do you define FIT? If you think about the FIT, there are two things which it matters, right? The starting point, which we define as a uniform distribution, and how we define the drift rate, right? These are the two things which will kind of help you define the FIT, which is the probability density function of alternative I to reach to the threshold by time t, right? So let's see. So this is the probability density function, which is, again, you don't need to understand this right now, but it is a function of basically the threshold, the initial starting point, and the drift rate, right? So this is all you need to understand, where di is the drift rate. And how do you define the drift rate, which is important, right? So MLBA is the most simplest model. So how it defines the drift rate? It defines the drift rates as a beta k times xik minus xjk, which looks very similar to utility, right? The drift rate looks very similar to the utility. And this omega ijk is a kind of way to define the attention given to the pair of alternative I and j on attribute k, right? So this omega I j k is a way to define how much attention you are giving to this attribute for the alternative I and j, right? So this is how you define the drift rate, and how they define this attention. If you don't have any attention data, then you make some assumption about how people pay the attention to the different attributes, right? This is how they define this omega I j k. So overall, what we are trying to say, there is this one aspect which talks about how the accumulator reaches to the threshold, and the second aspect we define the drift rate, which looks similar to the utility. In one of the papers that I'll mention lately, we show mathematically, if you make some assumptions on this model, you can show that this model is equivalent to the probit model, multinomial probit model. So you can easily show that, and we show that in one of the papers, and I'll indicate it when I talk about that. Because it's a much simpler model, because it's assuming the much more simplifying assumption on the drift rate. Now let's look at the MDBS model, that how we define really the MDBS model. So idea of MDBS model is, let's say you have a response time of, you split your response time in, let's say, 10 time steps, right? What MDBS says is, in each time period, the person accumulates the 1 unit of evidence in which of the alternative which wins that comparison that the alternative is having, right? So there are two aspects in the probability of MDBS. As I said, different models can be formulated by assumptions of how people are making decisions, right? And there is nothing right or wrong in terms of how you put the parametric forms. So what MDBS does, MDBS has the two parts in his probability. The first part is, again, probability of comparing two alternatives on an attribute in that time step. So the first part is more of the evaluation part, right? And the second part is probability of alternative I winning that comparison, right? And how do they define it? Probability of evaluating alternative I is based on the similarity of the attributes. That what they are saying is, two alternatives that they have seen and established in the using the eye tracking data, that two alternatives which have similar attributes are more likely to be compared than the other alternative which is present. And similarly, if you look at the probability of winning the comparison, they just use the logit type formula there, right? But here, in the similarity one, they have the attribute differences between the alternatives, and accordingly decide that which alternatives are more likely to be compared on an attribute. But this part can be easily augmented with the eye tracking data, right? Because this is about probability of comparing alternative. Now, I would like to give one more intuition that why this model will work better in explaining the decoy effect in Starbucks. Okay. So if you think about this model, it says that probability of evaluating two alternatives is higher if they are similar. So if you think about the decoy and the target, which is the medium coffee and the large coffee, they are more likely to be compared because their attributes are similar, right? In each comparison, right? And the probability of winning that comparison of the large coffee is much higher because it is better in those attributes. And both of these characteristics can be better captured by this model. The probability of comparison as well as the probability of winning that comparison are modeled here in this very explicitly. So I'll show you in an application that when you look at the effect of the decoy, revised MDBS just works so well because the MDBS model just works so well because it has all the ingredients to explain these complicated decoy effects or the other nudging strategies. Okay, so far, I know it's a lot of information for you, but so far broadly what I have told is, why do we need the models from cognitive psychology? How do they look like? Okay, how does their probability expressions look like? And now we'll try to understand, they are great, they can model the response, they can utilize the response time, they can use eye tracking information in their formulation itself. They can also be They can also explain the decoy effect, but why are people not using it, right? Why are still only psychologists are using these? The biggest problem is psychologists have used these models, but mainly in the lab-based settings, working with students on a very small scale studies, right? That's one major issue. Then second is, okay, we are using the response time, but what is the real value of the response time? What does it help in? So everyone needs an answer like, oh, you are using response time of the people, but what is the theoretical value of using response time of the people in modeling the decision making? They are not able to establish that. There are some empirical studies, but nothing, not real a solid study there. Finally, it's not very easy to incorporate the eye tracking data into these models because eye tracking data is very high dimensional. How do you incorporate that data into that model is challenging. And another issue is it's too much to collect the eye tracking data in the lab. So I'll go very quickly to each of these challenges and we'll see how we are addressing these issues. Just to be mindful of the time, may I know the time right now? 4:19, okay. So maybe 25 minutes, okay? In 25 minutes, I'll try to address that, how we address all these three challenges, okay? I would like to mention one more challenge which is not here. Estimating these models is very challenging, okay? Because they are dynamic models. They're modeling the whole decision-making process. So it's not as simple as writing the likelihood for multinomial logic model and just maximize it. It's much more complicated to estimate these models. So that's the fourth challenge which I'm not going to talk about, but we have been working on that. Let's go to the first one, which is the real world data. So we design a real world choice experiment because most of the people have used these models for the very traditional lab-based experiments. So what we did, we invited the ride-hailing drivers to our lab, and we also surveyed them out of the lab as well. But in Singapore, just to give you a context, that buying a car is very expensive. It's like $100,000 you have to just pay as a fee to have a car in addition to the cost of the car. That fee varies, but I'm just giving you a ballpark figure. So most of the ride-hailing drivers rent their cars for 1 to 2 years, basically. And then the idea here is we want to understand whether those people are interested in renting electric vehicles or can we nudge them towards renting the electric vehicles. So those who are currently using non-electric vehicles, we invite them to our lab and we try to see if we can nudge them toward the electric vehicle, okay? Renting the electric vehicle. So what we do, we first create their conventional vehicle that, okay, we invite to the lab and we ask a lot of questions about their fuel cost, driving range, all sorts of questions, right? And then we create the equivalent electric vehicle for them, right? And before introducing the decoy effect, what we do is we try to find an indifferentiable line where the electric vehicle and their non-electric vehicle become equally attractive to them. Because then if you introduce the decoy effect, in that case, the effect of the decoy is easy to estimate, right? So what we do is, for electric vehicle, we start with some price and we ask them that, okay, whether this is equally attractive to you as your conventional vehicle or not. And we keep changing this and keep asking them. And that's how we find an electric vehicle which is equally attractive to their current vehicle. Okay. After that, what we do is we use the same pair which is equally attractive to them, and then we kind of create the medium-sized coffee type situation. So what we do is we reduce this is the decoy effect, the decoy alternative that we introduce. And what we do is we reduce the driving range significantly for the decoy, like quantity in the medium-sized coffee. But we reduced electric vehicle for model B, which is the decoy. The renting cost we reduced very little, $20 and $50 out of $2,700. But we significantly reduced the driving range just to introduce the decoy effect in there, right? So this model B is actually the decoy, right? And daily operating cost we keep same for this decoy. Okay. So now let's look at the results quickly. So we define something called relative share of the target, that how the relative share of the target changes after introducing the decoy and before introducing the decoy, right? So it's like this is the relative share of the target, which is probability of target divided by probability of target plus probability of competitor. And when we look at overall, 0.5 means there is no effect of the decoy. Above 0.5 means there is an effect of decoy, but the number is very small, right? So what we did is we looked at the different groups. And when we looked at the different groups, class 1, class 2, class 3, and class 6, we could see the variation in RST. So some groups have higher decoy and some has no effect, right? So what we did, then we estimated different models like multinomial logit model and the MDBS model and the MDFT model, and try to see which of the models are doing better for each class. Interestingly, when the decoy is actually acting, in all those situations, the MDBS model was doing better. But when the decoy was not acting, MNL was doing better in the BIC or predicting the relative share of the target. So this is the first evidence that we have shown that in explaining the decoy effects, the MDBS and MDFT models do better job. And these are just some of the results, but we try to understand why do they do better. And to do that, what we do is we create these attributes. In the attribute space, we try to look at the probability of the target, and we try to see that it's highly nonlinearly captured by the MDBS compared to the traditional multinomial logit model that you see here. And these nonlinear effects are able to capture the effect of those decoys much better compared to the traditional MNL model. Okay. And the one more advantage, you might be thinking that why do we really need these models? The thing is, which we are trying to do now is, if you really have a very good model to predict the effect of the decoy, you can create the recommender systems, right? So you can kind of show the third option as a dummy option to nudge people to choose the option that you want, because you can predict that how that decoy will nudge people to the target alternative, right? So here, this is exactly what we show. We look at the different driving ranges of the decoy, and we look at how that changes the probability of choosing the target. And we find that if you keep the driving range of the decoy to be 50 kilometer lower than the target, then you can nudge people much higher compared to the other driving ranges. So it can be very useful in the situations when you are creating the online recommender systems. Okay, so this is a practical application. I would say psychologists also liked it. So I gave this talk to a psychology department in the University of Amsterdam, and they were very happy that someone is using their models in some practical studies rather than working with students. So it was interesting to them. Okay, here's a paper which published in Transportation Part A. You can get a lot of details about the experimental procedure, the estimation procedure. The code is also available if you want to know how to estimate these models. Okay. Second and third, I'll go very quickly. So I told you what is the value of the response time, right? It's not clear what is the value of response time. So what we did, it might be too much econometrics for you, but what we did is we defined the three distributions of the probabilities. First is the one, remember I mentioned when I was talking about MLBA, probability of choice and response time jointly. Probability of choice, if you have to compute, then you have to integrate out the response time. And then we defined the probability of choice given response time. This is something we thought is also an interesting way to see what response time is bringing to the table, right? And the point is, what we want to show is this CRT actually leads to the lowest standard errors. Because we have been saying that psychologists are using this response time, but what is response time really bringing to the table, right? So our argument is response time helps in reducing the standard errors, right? And how does it reduce the standard error? Let's try to understand that very briefly. Okay, so this is the math, but all this says is these all three estimators, which is the CRT, response time given choice, and the choice only estimators, follow the asymptotic theory, right? That means they have they converge to the sampling distribution, and the sampling distribution is Gaussian, okay? If they converge to the sampling distribution, they have this, you can say that the variance of the sampling distribution is actually inverse of the information matrix, right? So if you can say something about the information matrix of CRT, RTG, and the CO, then in that case, you can establish something about the standard errors, because basically you use these information matrix to compute the standard errors, okay? For multinomial logic model also, those who have written the code for the likelihood and finding the standard errors for multinomial logic, they will know that then you compute the Hessian, right? And from Hessian, you take the inverse of the Hessian, and then you take the diagonal of that inverse, and then you take the square root of that, and then you get the standard error. So standard error is obtained from this information matrix, right? So if we are arguing that all these three estimators reaches to the normal distribution with mean 0 and these information matrices inverse, then what we can see is then we can use the property of the information matrix to show what response time brings to the table. So there is a universal property of the information matrix. It is true for any joint distribution of the information matrix. So you can write this information matrix of X and Y as an information matrix of X given Y plus information matrix of X, okay? So if you can do this breaking, then for choice given response time, like joint distribution of choice and response time, you can break into the two parts, which is the information matrix for the choice only and information matrix of response time given choice, right? So you can think of response time as a X in this case, and sorry, choice only as an X, and the response and the choice as a Y, and the response time as a, sorry, choice only as an X and the response time as a Y, right? Similarly, you can break this into the other way around, where you have the information matrix of the response time given choice and at the same time response time and the summation, right? Because these all are the information matrices and these are positive definite, you can actually write you can assume that this part is also positive definite, this part is also positive definite. Then you can say that this information matrix of CRT is higher than the choice only, as well as the response time given, choice given response time estimator. And what does that mean? It means when you invert them, right? When you invert them, then you will have the lower standard errors for the choice response time compared to the all other two estimators that we have. And we do some simulation here for different parameters. So for different model parameters, you can see that I think here you have three estimators: choice only, choice response time, and choice given response time. And if you look at on the y-axis, you have the values of the posterior distribution of the parameters. And you can see the confidence or the credible bands are the smallest for the choice response time joint distribution compared to the choice given response time and the choice only model. So we do empirical study and simulation study as well to demonstrate that further. Here is a working paper where you can get all other mathematical details of it. Now, in next 5 minutes, I'll quickly talk about the one more work that we are doing. So I've been telling that having the eye tracking data is great, but how do you get it on a larger scale, right? It's very difficult to get the eye tracking data at a larger scale. So we thought that maybe we can conduct the small scale eye tracking study in the lab and then expand those insights to the larger online data sets, right? We don't know if it will work or not, but we tried it and it does a good job in terms of how we do it, right? So let's try to understand the process. So you have to think about the MDBS model that I talked in the very beginning. Remember, there was a one step where I told that the probability of comparing two alternatives on an attribute depends on the attribute similarity, right? But this is kind of an assumption that it depends on the attribute similarity, right? It might also be better explained if you have an information about the fixation data, like how people are evaluating alternative, or the fixation duration, or how people are doing the pairwise comparisons. So what we do is, in the probability of evaluating alternatives, we try to incorporate eye tracking data in that, okay? So for the lab data, we have this data, but for the online data or the data out of the lab, we don't have this information. So we have to find a way to transfer this information to the online data. How do we do that? This is just a formulation. So these are the 4 steps that we do. First, we do the same experiment in the both lab and the online data. Then we do the segment respondents. You can do any approach, but we just use the Gaussian mixture model because it is probabilistic. And for each of the class, we get the average attention matrix, like fixation counts, duration, pairwise comparison. We just get the average, right? And then what we do is, for the online respondent, we try to figure out the probability of that respondent to belonging to each class. And because we have the class-specific visual attention matrix, we use those probabilities and this class-specific matrix to compute for that respondent what will be these matrix by using the weighted average of the class probabilities, right? And these are just the details that you can look at later. And without going into the details of what classes we obtained, there are different models we created based on what eye tracking measures you use. So in the model 1, we use the fixation count. In model 2, we use the fixation duration. In model 3, we use the pairwise comparison, and in model 4 we use the pairwise comparisons and the fixation duration while defining the probability of comparing alternatives on an attribute, right? So before talking about transferring the information, we thought let's first look at what eye tracking data is doing to the lab data itself. So these are the results for the lab data, and what we are showing is the Bayesian information criterion, which is easy to understand. So you can see if you don't use the eye tracking data, but you just estimate an MDBS model, your BIC is around 280. And these bars are there because these models do not have a convex likelihood. So there is some uncertainty in terms of what initial values you do. So that's why you have these bars. As soon as you introduce the eye tracking data, even the fixation counts lead to a significant improvement. And if you use the pairwise comparisons, it's significant reduction in the VIC you see in there. And in the predictive performance in the effect of the decoy as well, you can see the errors decreases significantly when you include the pairwise comparisons, fixation duration. So with this, what we are only showing is that, okay, it works, the eye tracking data helps. But the next question is, can we transfer the eye tracking data to online? And then we try to see whether we really get some advantages there. So in the BIC value, this is the online data without any information on eye tracking. And here you see model 4 with the fixation duration as well as the fixation duration, as well as the pairwise comparisons. We see some significant gains in the BIC, as well as we see some gains in the ability to predict the decoy effect, but those gains are not so significant, but the model fit gains are still there. So all we are saying is there is a possibility to transfer information from lab data to the online data, but still it's a kind of a first study that we have done. We are trying to do other studies to see if there is a potential to transfer the information. And you can get the working paper here, where we are scaling the insights from the lab-based eye tracking data to the online data, where we provide all the details of how we do it. So in summary, I would say that there is a potential of sequential sampling models, but mostly I would say they are more valuable in situations of predictably irrational decisions where the nudging strategies are used. In the traditional settings, I don't think they would make a much of a difference. Like traditional discrete choice experiments may be not so useful. They would be as good as discrete choice models, but when there is a nudging strategy in work, maybe they are doing better. That's our experience so far. But they are not worse than the discrete choice models in situations when there is no nudging strategy. They are as good as discrete choice models. So this is a new direction that you can explore. You might have other ideas about using these eye tracking data sets and the response time data sets. Great, so I'm happy to discuss more afterward, but I think those, I have already stressed the session maybe 20 to 30 minutes. So I think I'll stop here and happy to discuss more afterward. Thanks.